everyone. Today we are going to start the chapter number 3. Okay. Just give me a moment while I start that software. All right. Cable, you can turn off your video. Yeah. Just a moment, everyone. All right. Yes, good evening. Okay. I hope now you all can see the screen. Okay. Right. So now chapter 3. See, this chapter 3 is is about current, right? So in the first two chapters we have studied electrostatics, right? We were talking about all those different situations where the charges were at rest, they were creating an electric field, right? Okay. In this chapter, that is chapter number 3, this is about current, right? Okay. Current, that is electric current, or it's about flow of charge, right? So in this chapter we are going to talk about what happens when charge flows, right? How can we make a charge flow and all the associated properties. And from here on we are starting a series of chapters where charges move, right? So we have finished electrostatics, chapter 1, chapter 2, electrostatics, done. Now, from here on, we're going to talk about different phenomena that happen or that occur when charges move, right? So first of all, we're going to study about electric current in this chapter. And then in chapter 4, we will talk about the magnetic field created because of electric current, right? And then so on and so forth. We'll continue about, the next few things, right? So right now, let's get started. લેગ થાય છે પણ હજી કઈ લખતો નથી. હજી મેં કઈ લખ્યું જ નથી. Okay. So people, please come on time. Chapter 3, electric current. Okay. Yeah. I don't know what is the name, current electricity or electric current. I don't. Yeah, sorry. The name of the chapter is current electricity. See, I don't even know the name of the chapter. All right. Okay. So in this chapter, like the name suggests, we are going to study about current. So I'm sure you have studied this definition, right? A lot of this chapter has been done in 10th, right? So you'd be, I'm hopeful that you'd be remembering a lot of things, right? So current is defined as the rate of flow of charge, right? Electric current is defined as the rate of flow of electric charge, right? So the formula for that electric current is dq by dt, right? Okay, so this is actually a very basic way to write what it is. If you want to write it very properly, I mean perfect, it is the rate of flow of charge flowing across a cross section, or flowing across, you could say, an area, right? Flowing across a cross section per unit, or rather, yeah, that's it, right? Rate of flow of charge flowing across a cross section, right? So it means that suppose this is some wire, right, in which current is flowing, or in which charge is moving or charge is flowing. Then if you mark one cross section, let's say here, then in unit time, how much charge will cross from one side to another side, or other side to this side, either way, right? It's actually supposed to be net, that is total charge flown. All right. Okay, so anyways, the current I is defined as dq by dt, that is the rate of flow of charge across a cross section, right? So if dq is the small charge flowing in some small time, dt, right? So that's how it is. Generally, if current is constant, if current is constant, then we can also write this formula in this manner. This is what you had in 10th standard. And 10th ma differentiation not out, right? You could also write this as like this, right? Delta q by delta t. All right, well, delta q is charge flown and delta t is the time interval that it takes. All right, so remember that this is the most correct or perfect definition. All right, okay, આ બધું પછી એમાંથી આવે special cases, right? But yes, don't be shy of using this, right? We will use I equal to q by t many a times, right? Because often we are going to talk about constant currents, right? So that is it, right? So a very quick basic question to go through, right? Unit તો આવડે ને, એમ્પિયર ને એવું, right? એવું તો શીખવાડવાની જરૂર નથી ને, that unit of current is ampere, symbol is A, and 1 ampere is 1 coulomb per 1 second. ઓકે, આ બધું 10th માં આવશે, એ તો હું સ્કીપ કરીશ. જરૂર પડે તો તમે પછી જોઈ લેજો તમારી રીતે, right? Because a lot of things are exactly like they were in 10th standard, right? Okay, so let's try this one quick question. Suppose this is some kind of tube, all right, and in this tube electrons and protons are moving. All right, electrons and protons are moving. Okay, so let's say I mark one cross section here, right? Okay, and if I tell you that in 1 minute, 1 mole electron go from left to right. Okay, suppose I tell you that in 1 minute 1 mole electrons go from left to right, and in 1 minute at the same time, okay, both of these are happening together, right? At the same time, half mole of for example, let's say H plus ions go from right to left. All right, let's say that in that 1 minute, half mole of H plus ions go from right to left. Okay, so આ ચાર વસ્તુ છે, અહીંયા ધ્યાન રાખજો. So what is given? Electrons are going from left to right, and H plus means protons actually are going from right to left. Okay, then how much is the current flowing through this cross section? That's what you have to find, right? આવું કરવાનું કીધું હોય. So first of all, what we'll do is, in 1 second or in 1 minute, પહેલા minute નું ગણાકે, in 1 minute how much is the charge flowing, right? Okay, so let's talk about that. See, I'm sure you remember that flow of positive charge is considered positive current, right? Okay, so what I mean to say is we can say that here H plus ions, they are going from right to left. So how many H plus ions? Half mole, right? How many H plus ions? Half mole. All right. So half mole is 3 into 10 raised to 23 H plus ion, right? And how much is charge of 1 H plus ion? How much is charge of 1 H plus ion? Avde ne? Charge of 1 H plus. Come on, people. What is the charge of 1 H plus? Yes, it is same as the magnitude of electrons charge, right? H plus એટલે proton, ભૂલી ન જાઓ, chemistry. 1.6 into 10 raised to minus 19 coulomb. All right. So this is the number crossing in 1 minute. This is the charge crossing in 1 minute. But there are also electrons going over there. But see, positive charge coming from right to left and negative charge going from left to right, that will add to it, right? Okay. So plus how much charge, how many electrons are going? 1 mole electrons, right? Okay, so that will be this much for the electrons. I hope you understand why. Suppose there was zero charge here and there was one proton here. If it would go there, then here there will be plus one E charge. And similarly, at the same time, if there was one electron here and it would go there, so now finally two E charge has flown, right? One E from here to there, one E from like that. Okay, I hope that makes sense. Divided by 60, right? Because this is in seconds, right? આ તો થોડું complicated થી ચાલુ કર્યું છે. All right, don't worry about it, right? All you have to do is you have to find how much charge has flown. So આટલો થયો flow and then you divide by time, right? So this is going to be your answer. 60 seconds કર્યું, 1 minute, right? So please remember that direction is important for current. Direction is important. If you think of one electron, no, sorry Chaitya, I will not explain it again. A tenth નું શું બીજી વાર explain કરવાનું? Look at this carefully, everyone. I'm saying direction is important. Suppose one electron will go from here to there, right? Okay, and in the same time, if one electron goes from here to there, then total charge flown is zero. I hope you understood that, right? Because if one electron will go from here to there and the other electron will go from here to there, right? So that would cancel the flow of charge. I hope that example is clear, right? So what I'm saying is that the direction is also important, right? Chaitya, this 3 is for half mole. Right? Does this make sense? Did you understand this one? Did you understand this one? If one electron will go from here to there, and in the same time one more electron will cross it in opposite direction, then the total charge flown will be zero. Can you hear me now? Okay, fine. So there was a internet problem. Okay, so I was saying that if you consider a situation, let me just put that point once again. I was saying that if you consider a situation like this, where you talk about this cross section, let's say that there was one electron here and there was one electron here, right? And if in some time, okay, in some time t, if this electron would flow across this and this one would flow across this, then the total charge flown would be zero, because the motion of one electron from left to right, okay, has effectively cancelled or neutralized the effect of one electron moving from right to left. So that's why I was saying that the direction of flow is important. Okay, so in such a case the current would also be zero, even if the charges are flowing, but still the current is zero, because current is defined as the net flow of charge, right? The total flow of charge per unit time. Okay, if you want to write it like that. Okay, it is the net or total flow of charge across this cross section per unit time, right? So please remember, direction is important. All right. Okay, so just taking that further, if 1 coulomb charge would flow from left to right and 3 coulomb charge would flow from right to left, then the current would be 2 coulomb per second. Suppose this is time is 1 second. All right, then this would be 2 coulomb per 1 second. I hope you got this two, right? 1 and 3, but they are in opposite direction, right? So this is 2 coulomb per second or 2 ampere. Okay, तो आज मेन वस्तु समझવાની છે, right? Okay, now uh, with that done, let's go to the next thing. Let's go to the next thing. Oh, so sorry, there's a white pen. Okay, so now we go to next thing, current density. All right, now we are going to talk about the next thing, which is called current density. Now what is this current density? Here its definition: current flowing per unit area of cross section, right? Current density means current flowing per unit area of cross section. All right, so what do I mean by this? Let's take an example. All right, symbol ને એવું બધું કહું છું હમણાં, પહેલા example. Suppose this is a wire. All right, okay, this is some piece of wire, and let's say this wire's cross section area is 1 mm square, for example, right? So this area is 1 mm square, right? And let's say that in this wire there is flowing a current of, let's say, 2 ampere. All right, then the current density, symbol of current density is J, right? uh, just check whether your book uses lowercase j or capital J. I'm not so sure, because some books use it this way, some the other way. I think it is lowercase. Okay, in this book all that is explained much later. Never mind, lowercase j. I just checked it out. It is lowercase j. All right. Okay, right. ચલો કઈ વાંધો નહીં. Now the interesting thing about current density is that it is a vector, right? This current density is a vector, all right? So it has a direction as well. Now see, a word of warning: current is a scalar. Current is a scalar, but see, this has always been a confusion. I'm sure you know that you can say that if this is a wire, then current is flowing like this, right? Or maybe like opposite. So current does have a direction. I'm sure you have seen that when you did such things in 10th standard, you used to say that current flows from here like this. Agreed? Do you remember that? So current also has a direction, but still current is a scalar. I know that's very weird, right? Okay. I later I will tell you why it is like this. Okay. The answer lies in maths, right? It's not a very tough thing to understand, right? But this is not the correct time to explain. Okay. There is a reason, Kodal. I will tell you, right? Okay. Yeah, Chaitya, you could say it is a pseudo vector, right? Some people like to use that term, pseudo vector. But why is it not a vector? That is what I'll tell you later in the chapter. Okay, it comes in the chapter only, right? It's not like I'll leave it for later. Its direction is fixed from positive to negative of what? I could reverse the battery, then the direction will change, wouldn't it? So that's why you can't really say that its direction is fixed. It would change. It would now flow like this, right? Okay. So current is a scalar, right? But it still has a direction. Actually, some people like to call it, it has a sense that is either this way or that way, like that. Okay, but anyways, more about it will come later, right? Okay. But current density is definitely a vector. All right, let me tell you, everyone. Current density is definitely a vector. All right, so it has a proper direction. And the relation between current density and current can be written like this in scalar form, but I'll warn all of you. I'll warn all of you that normally this is right, but the most perfect way to do it is as follows. Okay, this is the proper way to write current. All right, current is integration of j vector dot dA, right, or integration of j dA cos theta, right, where as usual theta is angle between area vector and current density, right? That is, it is angle between dA vector and J vector. All right, પણ તમારે છે ને આવા સમ લગભગ ક્યાંય આવતા નથી કે જેમાં આવું બધું કરવું પડે. All right, so if current density is uniform, right, if current density J vector is uniform, જો ઓલું electric field જેવું જ આવ્યું ને. શું લખ્યું કઈ ખબર ન પડી મને. So if current density is uniform, then you can write I is equal to J into A, right? I don't think you'll have any problem with that, and JA cos theta. Right? Normally, in most situations in your book and even in JEE, right, એટલે NEET માં આવી ગયો એમાં બેની વચ્ચે, in most situations theta will be 0. All right, કેમ સમજાવું તમને. If you draw a diagram, let's say this is a wire. Typically we take, oh, sorry, you won't be able to see it. Typically we take this kind of cross section. તો આ cross section લઈએ ને તો એનો area vector કાં તો આમ આવે કાં ઊંધી બાજુ આવે, બરાબર. So if current is flowing in this direction, okay, if current is flowing in this direction, right, we typically take current density also in the same direction. તો પછી angle થઈ જશે 0, right? So you get I is equal to J into A. A is area vector, all right, or area, simply cross section area, right? What is it, Jay? Okay, so sorry, let's continue. Current density is current per unit area, right? So that's what I, definition તો ઈ જ લખાવી જોવો ને, આ શું definition લખાવી, બરાબર ને? So current density is current per unit area only, બીજું તો કઈ છે જ નહીં, right? And everyone, I will not send you the whole board work today, right? આપણે એવી સિસ્ટમ પાડવાની જ નથી. લખવું હોય તો લખતા જજો. I will not send you everything today. Is that clear? કે હું જો તમને લખવાનું નહીં કહું તો તમે બેઠા જ રહેશો, ખાલી સ્ક્રીનશોટ પાડીને હા બસ છે આપણા ફોનમાં પડ્યું છે, એવું બધું કોઈ નહીં કરે. Okay, so like I said, typically we'll have it this way. એટલે જો બોર્ડ એક્ઝામના કોઈ ક્વેશ્ચનમાં મને નથી લાગતું કે તમારે આના સિવાય કોઈની જરૂર પડે, બરાબર. બહુ તો વેક્ટર ફોર્મમાં આવી રીતે લખી શકો, right? Okay, so these two are actually enough for board exam, right? These two are actually enough for the board exam, right? એના સિવાય લગભગ કઈ જરૂર પડવાની નથી. Okay, so what do you think is the unit આવડે ને, unit of J? What do you think is the unit of J? It will be coulomb, ampere per meter square, right? Okay, it will be ampere per meter square, right? એમાં તો કઈ અઘરું નથી. Okay. Now let's continue with the next thing. See, you might have a question like, what's the need of J, right? I will answer that question after. Yes, Kodal, it is always right, but તમારી બુકમાં એટલું બધું ડિટેલમાં છે નહીં ખરેખર. કરંટ ડેન્સિટીની ચિંતા નહીં કરો ને તોય ચાલશે. I equal to J થી જ બધું થઈ જશે, તમારે સમ્સ એવા જ આવે છે, right? Okay, it's actually valid for any kind of shape, right? So what's the need of J? That we'll talk about after talking about Ohm's law, right? Okay, so let's start now. Let me just take a minute to clarify that in this chapter we are going to talk about metallic conductors. Metallic conductors એટલે wires and everything which are made up of metal, all right? In this chapter we are only going to talk about metallic conductors, right, as far as all this is concerned, right? Now, so I'm sure you have studied the Ohm's law, sure you have studied the Ohm's law, right? Okay, so we are going to talk about that, right? So just before that, just before we go on to Ohm's law, let's define or let's understand what is resistance. Let's talk about what is resistance, especially for metallic conductors. Uh, you need to develop a rough idea of what resistance is. It is based on the free electron model, right? It is that typically in metal, this is what we have, right? That there are lots of ions, but the electrons, they are free electrons, right? That is, the electrons could actually go anywhere. Electrons could actually go anywhere inside this metal, all right? Okay, and they don't typically belong to only one atom, right? They are just like they are shared electrons. They are not. It's not a covalent bond. Again, by sharing, I really mean that they are common for all of these atoms, right? So electrons can actually go here or here or here or anywhere, right? They can flow, right? That's why they are called free electrons. Now, the thing is, when they try to flow, right, due to the random motion in everything, in every ion or for every electron, right, there's obviously going to be random motion. So what happens is, because of the random motion, these moving electrons will often collide with the ions, right? I repeat, the moving electrons will collide with the ions, and this is what stops or obstructs their flow, right? I'll repeat, you could just say that the of free electrons, motion of free electrons is restricted, okay, right? Restricted, or you obstructed, if you understand that word also, obstructed. Obstruct, that is to come in between, right? Due to collision with the ions in the metal, right? So this obstruction is what is called, oh sorry, this obstruction is what is called resistance, all right? Okay, so what happens is, when the electrons try to flow, there will be a resistance, right, to the flow, and that is what appears, or that is what is wastes energy, right? I'm sure you understand what I'm saying, right? When the flow of the electrons is obstructed, there is a collision occurring, and in such processes some energy is wasted. So so that phenomena is called resistance. Now, let me also tell you one thing. What I've taught you over here in this particular page is actually the old or the classical view, right? This is old or the classical view. This is not perfect, all right? Okay, the proper explanation is coming from quantum mechanics, right? And that we don't have to study, okay, right? You don't have to study the perfect or the proper explanation of resistance, right? Okay, that's not a part of your syllabus, right? This is just the classical view or the old view, all right? So it's not totally wrong, it works very well, right? But it's a bit weird, given the recent that is, uh, what we know in the last 100 years about electron, right? If you consider all that, then this is nonsense, right? કંઈ કહેવાની જરૂર નથી, કંઈ કહેવાની જરૂર નથી, હજી તમને એમાંથી કંઈ જ ખબર નહીં પડે, right? Okay, so it's not worth to talk about at the moment, right? લાસ્ટમાં છેલ્લે કઈ સાવ છેલ્લે બધા ચેપ્ટર પૂરા થાય ને ત્યારે વાત. Okay, now so let's go to Ohm's law, right? See, most people get Ohm's law wrong. Please be very careful, everyone. Okay, some of you think that this statement or this formula is Ohm's law. Okay, that's wrong. This is not Ohm's law. All right, so then what is Ohm's law? Ohm's law is this. This is the Ohm's law in short. All right, V proportional to I for metallic conductors is the Ohm's law, right? V equal to IR is not Ohm's law. Okay, please remember that. આ છે ને તમારે તો સેમિકન્ડક્ટરમાં આવું આવ્યું હશે. Frankly, this is used for diodes. હું ડાયોડનું થોડુંક તમને યાદ કરાવી દઉં, right? Diodes have something called resistance defined like this, right? Okay, so you can clearly see that this kind of relation is valid for diodes also, but truly speaking diodes don't follow Ohm's law, કારણ કે આ Ohm's law છે જ નહીં. Ohm's law આ છે, right? V equal to IR is not Ohm's law. Please be careful. V proportional to I is Ohm's law, right? Okay, so let's write it properly or formally. Under certain circumstances, all right? So what are certain circumstances? Constant external factors, right? Like temperature, pressure, all right? So under certain circumstances or under constant external factors like temperature, pressure, the current passing through a metallic conductor is proportional to the potential difference across its ends. This statement is Ohm's law અને આ એનું mathematical form. Okay, this statement is Ohm's law and this is the mathematical form. V proportional to I. Okay, now let me make it very clear that this law is empirical. What is meaning of empirical? I think I have told you many times. Can you tell me that? What is meaning of empirical? હિમાની કરેક્ટ. ચલો એક જણનો જ આન્સર આવ્યો. ભૂલી ગયા તમે લોકો એમ્પિરિકલ? નો તનય, નોટ એટ ઓલ. સિમ્પલ ફોર્મ ને એમ્પિરિકલ નો કહેવાય. નો નો નો, યુનિવર્સલ ઇઝ નોટ એમ્પિરિકલ. અરે empirical means obtained or observed from experiments. Okay, empirical means observed from experiments, right? But at that time without knowing the reason. Okay, without knowing reason. બરાબર ને? આ empirical કહેવાય, right? Okay, so let me be very clear. Ohm measured such things, right? He measured V, he measured I, and found that V is proportional to I, right? He found that V is proportional to I. For what? For metallic conductors only. ગમે તેના માટે નહીં હો, diode માટે નહીં, right? For metals only, right? અને એમાંય તે આ બધું constant રહેવું જોઈએ. Okay. But he didn't know why. Frankly, he had no idea why this was happening. All right. Okay. Also, let me tell you this. That this form V proportional to I, we are going to call it macroscopic form of Ohm's law. Okay. We're going to call it macroscopic form of Ohm's law. All right. Why macroscopic? I'll tell you why it is called like that. Because we can measure things given here, right? We can measure both of these things directly, right, by using instruments. All right. Later on, we are going to talk about another form of Ohm's law, right, which will derive from theory, and it will use such things that we cannot measure, right, on the inside of the metal. All right. I'll repeat. We will derive, or we'll talk about another form of Ohm's law, which will have quantities that you cannot measure from inside that metal wire. All right. Okay. Right. Now, of course, the last well-known step is if you remove the proportionality sign. If you remove the proportionality sign, see, you could also write it like this. Okay, એમાં કઈ ખોટું નથી. I hope you realize that there is no difference between this and this, right? Okay. So the last step is, if you remove the proportionality sign, we should write a constant. Okay, so that constant is called R, or resistance, right? R is the resistance. Okay, clear? I hope that makes sense, right? Okay. Right, R is the resistance. Its unit is ohm. આ બધું કહેવાની જરૂર છે. This is its symbol, right? This is ohm symbol. All right. Dimensions તમે જાતે find કરી લેજો. See, this is a hot favorite question. ગુજસેટમાં, બોર્ડ એક્ઝામમાં આવે જ છે. Find dimensions of R. Okay. Please do it on your own. એવી રીતે હા, dimensions of capacitance એ find કરી લેજો. Everybody, ત્યારે હું કેવું ભૂલી ગયો, અત્યારે મને યાદ આવ્યું. Please find out dimensions of capacitance. Okay. ગોખીને રાખજો. રે તો નો યાદ રહે તો કઈ વાંધો નહીં, તો પછી આ તો થઈ જ જાય. R equal to V/I કરતા તો આવડે જ ને પછી. Okay. Right. Now let's talk about a little bit about resistance. Right. Let's talk a little bit about the resistance. પછી માઇક્રોસ્કોપિક ફોર્મ ઓફ ઓહ્મ્સ લો પર આવશો. અત્યાર નહીં, આ મેક્રોસ્કોપિક ફોર્મ આવી ગયું. હવે પહેલા રેઝિસ્ટન્સનું થોડુંક સમજાવી દો, પછી માઇક્રોસ્કોપિક ફોર્મ. I don't want to know the answer, Harsh. In fact, even I don't remember. I'll have to verify it. Okay. So resistance, let's talk about that again. But this time we are going to talk about resistance depends on what? Okay. What does resistance depend on? All right. So you may have had some idea about this. 10th માં આવતી હતી formula, R equal to એવી કઈ. Do you remember? Did you study any such thing? A formula of resistance? What is that formula? Okay, very good, Avinash. Yes. Yes, Kea. જો આવડતું હોય તો મારે શું કામ ફરી વખત સમજાવવું જોઈએ? હું તમને એટલે પૂછું છું. બરાબર? Are you sure only 2 of you know it? Very good, Purvendra. 3. No, Sumit, it is wrong. No, Vishwa. Yes, Christy, that's right. Yes, Joy. No, Deval. No, Harsh is not correct. તો તો કંઈક બીજું જ લખે. No, Vishwa. Yes, Krishraj. નહોતું આવતું તમારા લોકોને 10th માં? આટલા લોકોને તો આવડે છે. આવતું જશે ને. The formula is this. Yes or no? Right, everyone? આ તો યાદ જ હશે. હતી ને યાદ? Okay, fine. No problem, no problem. So see, even this formula, remember, this is only true for metals. Okay, first of all, this formula is only true for metals, or actually you could extend it a little bit. You could say this is true for crystal lattice solids. All right, or you could say uniform solids. All right, I actually mean to say uniform solids. All right, this doesn't work for gases, this doesn't work for liquids. All right, now this formula is also empirical. This formula is purely empirical, right? But this one is actually very easy to understand how people would have obtained it, right? This is very easy to understand about how people would have obtained it. So this is the way. See, what people would have done is, listen to this very carefully. It's that, suppose you take two pieces of identical metal wire, right? Suppose you take two pieces of identical metal wire. All right, okay, બધી રીતે identical. All right, so what's the length? Let's say L. So this is also L. What's the cross sectional area? Let's say A, right? Okay, suppose આને wire 1 wire 2 કહી દે, બરાબર? એટલે મારે A લખવું હોય તો લખાય. So then people did such kind of experiments as I'm going to describe in these remaining 5 minutes of the class. They took one wire, okay, they took one wire and connected it with a battery and measured the current, right? They took one wire like this and connected it with a battery and measured the current. Okay, then they took both the wires and connected them back to back. So now it was like a longer wire, right? Double length. I hope you understand what I'm saying. Okay, I hope you realize that now we are talking about double length. So then they noted that when we take double length, okay, when we only change the length and we double the length, right, we see that if we double the length, the current is half, right? We see that if we double the length, the current becomes half. Similarly, what they would have done is they would have connected like this. Okay, I hope that makes sense, right? Like this means one on top of each other. So now this is double area. I hope that makes sense, right? It's like charge can flow through this, or it can also flow through this, right? So it has double area, right? So when they took double area, they noted that current was double of what was original, right? So this is, such kind of observation makes it clear that what happened here is, why is the current half? If you consider the Ohm's law that V is proportional to I, and then based on that you write V is equal to IR, right? The battery is still the same, right? We are not changing the battery voltage, all right? So battery is still the same, right? So the idea is that when we double the length, the current is becoming half, but this is same. So that is only possible. That is only possible if R is double, right? I hope that makes sense, right? If current becomes half, that's what they would have observed, right? If current becomes half, then R should be double, right? So what we are basically talking about is, if you double the length, then resistance is also doubled. And similarly, if we double the area, the current is doubled, that means resistance should become half, right? I hope that makes sense, right? So if that happens, if resistance is half when area is double, so both these properties together tell us as follows. This one tells you that R is proportional to length. If you double the length, R is double, right? And this one tells you that if you double the area, R is half, right? So this is what we get. Okay, is that absolutely clear? Right? See, there are ways to explain why. See, if anything is empirical, we must always ask a question: why is it like this? Right? Why has nature made it like this? Why did nature not like this? Okay, right? I don't like R proportional to L. I want nature to have R proportional to L cube. So what's the reason why you have this, right? So we'll try to explain that reason, but that will come a little bit later in this chapter. All right, it will come in this chapter only, but you'll have to wait for it for a while, okay, for a few more topics. Okay, so again, it is that if you combine both of these, you get R proportional to L by. But I'm sure you understand that how much current flows should definitely depend on what you are connecting here. That is, what is this wire made up of, right? Okay, whether it's aluminum or whether it's copper or whether it's silver or gold or something else, right? Maybe wood, right? So what I'm trying to suggest is that apart from length and area, cross section area, remember A is cross section area, right? Apart from length, yes, Sorali, that's right. Apart from length and cross sectional area, it should also depend on what's the material, right? It should also depend on material. So that's why when we remove this proportionality sign, we write something called rho, right? Where rho is dependent on material and rho is actually called the resistivity of material, right? Rho is called resistivity of material, and resistivity does not depend, I repeat, resistivity does not depend on length or area. Okay, resistivity depends on temperature. Resistivity depends on temperature. All right, resistivity depends on temperature. Okay, it does not depend on length or area. It's a property of material. I repeat, resistivity is a property of material. Okay, yes, right. Specific resistance. No, actually, Vraj, the word specific resistance, as far as I am aware, specific resistance is resistance per unit length. right? But I also remember that different books in physics and chemistry, they actually define this in a different way. All right. So I would actually say that before I confirm it how it is given in your textbook, you don't really worry too much about what is specific resistance. All right. Okay. ના ચૈત્ય 1/r એટલે કંઈક અલગ જ વસ્તુ થાય, બરાબર? ખોટું ઈ બાજુ ન જાઓ. Okay, so I'll tell you about specific resistance. Don't worry. What's given in your book, that is important for us, because like I've said, I've seen that different chemistry and different physics books use different meaning of this word, right? એ confirmed જ છે, right? જોયેલું છે નજરે કે અલગ હોય જ છે, right? So we will follow what is given in your textbook. If it is not given, don't worry, right? All right. So please remember these things, right? So just one final remark before we finish this. Resistivity is very high for insulators. Okay. Resistivity is very low for conductors. All right. Like metals. Right. Okay. And resistivity is moderate. Moderate, that is medium. Okay. Not so low, not so high for semiconductors. Okay. No, if I will be double, then R will be half there. If I will be double, R will be half. All right. So these are some properties or important things about resistivity. Okay. So with that, we are going to stop over here. All right. Goodbye, everyone. See you all tomorrow.